Yep, so now there are 3 people joining. Should be a lot more. So we'll wait a little bit and then we'll start. So somebody is asking about the column. So we're gonna make a new one, I think. And we'll look at the previous one. And then, so the goal is for today is to get to the point where we actually can implement this using the template that I gave you 2 workshops ago. But in this case, hopefully we will understand why the template is the way it is. And yeah, today we're gonna implement the task that I gave you for home, and nobody did it. So I assume that you don't understand it, and we'll try to make it slowly, and we'll explain it. And if there's questions, then please write in chat and stop me. So now we have 7 people. Let's wait a little bit more. Hopefully there should be more. I know that there should be at least 2 people from Riga today. 2 of the students. Is anyone in the live from Riga right now? If you are, then please type in so I know that you are actually here, because you should be here. If you don't type now, then I will know that you did not join this session. So there should be 2 people from Riga, at least 2. And the others from Ventspils. As we're having this in English because there are at least 1 person or 2 from your group speaking English. So right now I see 6 people. No one from Riga typed in the chat, so I assume that they told that they will join and they did not join, I guess. But that's on their own problem. Okay, so 1 is joining. 1 joined. Okay, Alice, so that's good. Seemed like David's did not join. He should join. So anyways, so I shared the links. Now we are 7 people. Maybe wait few minutes more and then we'll start. just to reiterate, we gonna get to the point where we continue working with the template I gave you yeah, 2 sessions ago. Nobody handed in the homework last week, so it seems like that you didn't understand it. And yeah, and then hopefully from the template that we'll do on the Python itself, not on the notebook, you will be able to finish some of the tasks today and also in home. So if you don't do any tasks at home, it's very likely that you will not understand how to do this stuff. Like you need to try to solve it your own way. Also, okay, 8 people. So I highly recommend to do these things at home. Okay, so 9 people. Okay, let's wait a little bit. So just to show the notebook and the homework was there to, so it was defined here basically. So you should have made the model that is with a sigmoid over the whole stuff here. We even gave you the derivative of the sigmoid. And what else? So here is the e minus x, right? And yeah, and so we did some couple of steps of optimization. Today what we're going to do is we're going to try to make that model from scratch, and we'll make the code a little bit more like so there should be training loop and stuff like that, so that's not we don't need to run the cells many times. But still, because there are at least one person who promised from Riga joined, so that's why we'll go quickly also through the equations. And I guess because nobody gave the homework, then it seems like that you don't understand it, and we need to do it also. So anyways, so make a new notebook. You can use the previous one if you want to copy some of the stuff. Maybe you can clone it, so it's a little bit easier to make all of the stuff. So let's start with some of the equations. Maybe I can copy it as well and then expand on that. So you can do this as well. So regarding the equations, so let's try to make it very simple. Try to make it clear. So okay, if you have G, F, so I will maybe okay, I will move this stuff here on the other screen so I don't distract you. Okay. So we'll have again the problem. So let's try. So this first cell will gonna be the problem cell. Okay. So tag. So this is gonna be the problem data set. Data set. Okay, I don't like this cell. Again, the same problem. As I said, you can copy it or write it down as you wish. So let's say we'll have the X data set. And this will contain the values. This will contain, so this X is going to be the number of floors in the house. 3, 4, 2, 3, 5. So this is like the so yeah, let's write floors in a house, and the y is the price of the house multiplied by 100k euros. Let's say that doesn't matter. It's just like example to give some kind of illustration of why the this function graph is necessary at all, basically. So I'll have those two things. I'll keep an eye. I'll try to keep an eye on the YouTube chat as well, so you can drop in if something is not clear. Okay, this is our problem. That's it, right? we have 3 samples basically. we have 3 samples. Want to be able to predict, let's say for x 4. So like x, this is going to be x4. So what would be the price if the x would be 4 floors, for example? So that's what we want to predict. So we need to train model that can do this, or predict any other type of, let's say, floors. So this is like our relationship. The input, of course, can be multidimensional. Now there is only like floors, but we could take, let's say, the number of rooms in the house. So we could have for each data point 2-dimensional input. We can have output as well, 2-dimensional, 3-dimensional, whatever. So now here the model plus loss basically is the function graph. This is what we're gonna solve, and what will provide us with the answer. So I can copy that. So I will rewrite it from the homework that we had, basically. So again, for the partial derivatives of the functions, you can of course open everything, but like it's recommended that you don't open it, but use chain rule. So we're going to do this again. So g function, okay, this is a g c dot x. So this is well, like one part of our linear layer. Then the other part would be, let's say, f is going to be x w b. This is then g of when x w plus b. So this is going to be like the full linear layer, the proper linear layer f. So the parameters, maybe I can somehow mark them. Okay, let's write it like that. So the parameters theta, so these are, actually maybe I could write these lines. No. Okay, let's do this. Okay, cool. So the theta will be WB. Not sure. Let's see. I will check if we need some other parameters. So now we have 2 parameters. So let's see if I can get a new line. Okay, we can. Okay, cool. So so far the model. Then the next layer that I had in homework, basically. So what I had in homework, there were some additional layers that we added. So we added sigmoid, I think. Yeah, so the next one is going to be the sigmoid layer. Yeah, so let's write sigma. Again, this guy will take. So sigmoid layer is not a parameterized layer. The function layer and function, I use those names intermittently, like, but they're basically the same. So frac 1 over 1 plus e in the power of minus basically. So it's basically the f function here, but it would not be nice to write it there, but we need to write it there. So x v b. So that is the input there, right? Yeah. So like that. This is the sigmoid then. Yeah, the sigmoid then covers that part. Okay, it's maybe we should not call it sigmoid, because sigmoid is not actually dependent on those other values. maybe let's call it just h function, right? But it is sigmoid basically. The sigmoid is without any parameters. As you see here, the b is parameter, w is parameter, but inside here there is no parameters. There's just a reference to the next function in the function graph. So just to reiterate, the x is the input, like the floors of the house, and the final output of this function graph that we are writing will gonna be the y, the prediction of the house price. Okay, so let's see then the next stuff that I had there was the r. So let's think. So maybe I can just add it here directly. So the r would be like some kind of scalar. And this is also not learnable parameter, but hyperparameter. So the r is the maximum value of so over I over yi. I think I even can hopefully add there. So it's like just a scalar to help the convergence. So basically it means if we use this kind of model, then we are limited to the 9.5 maximum value for prediction. If we want larger value, then we need to replace r with larger value, but basically that's just an example. So okay, we multiplied by r that stuff. So that's our model basically. H is our model. So the output of the h would be y prime. So that is what we want to predict. So this is good. So this is our model. This is what we want to predict. And the loss function, the function that will give us the error that we want to take in account to change the weight and bias, the learnable parameters theta, to change them in some direction using the loss function. In this case, let's give it again the mean squared error. So the loss function. So the loss function in this case is going to be so the y will be the ground truth value, and then there's going to be the so all of this stuff, and it's going to be the in this case let's write it without the summation. So y minus h, this is y prime as you see, so h in the squared, right, like that. So cool. And yeah, basically the main task now is to find the weight and bias, those values, so that it would work. So okay, cool, I see the question. Why does the h have two different outcomes? So it don't have two different outcomes. It just means that the this equation produce the same output as y prime. So I can just write it here like this. So this is the same thing basically. Maybe it's even, yeah, maybe if you have such a question it's not clear maybe. So you're trying to predict the y prime, and now the tricky part comes that we need to add over the h, our model. So yeah, over the h, the model, we need to add the loss function, the last layer, that is actually not the part of the prediction. Basically, when we will have the trained weight and bias, the weight and bias that we will find, like we will know what is the best values there, then we can throw in trash the loss function. It doesn't need to be there. It's only temporarily, so only during the training. So only during training we add a loss at the end. So Christopher's, really thank you for asking the question. That helps me to guide this conversation in the right direction, so we don't, like, I'm not talking to myself. So, and the model that we can use after training is this. And also for evaluation, you know, like we can calculate what is the some error or mistake that is not related to the training itself. So okay, that's parts. Okay. So the loss here, as Christopher has pointed out here, the y prim is the same as the output of that function. So for the easier derivative, like we could rewrite this just as y prim, all of that stuff. So y prim, and then it would be very simple, like y minus y prim squared, right? But before we do that, let's reiterate what we want to do actually. So we want to find the best W and best B value. To find that, we will use the temporarily loss function. So, and what we want is to have the partial derivative, the direction in which we need to change the W to get it better, to reduce the error, basically, to get error to the zero. So to do that, we can formalize it by writing this stuff, and by the partial B, like this, right? So yeah, so this is what we want to find, basically. We want to find this guy, and we want to find with regards to B. So if you find those two values, then what we can do next is we can change the V and bias. So W and bias. So to change the W and bias would be W. So this is going to be our new W, I guess. So let's call it W prim. So W minus W alpha times C dot this whole stuff, like that. So yeah, so we can change the W, and if we change this enough times, we will get very low loss value, close to zero, and the Y prim automatically will get better and better and better until it gets the exact like very close results to what we want to see there. So the same goes with the bias. We do the bias as well the same way, like this. So this is how we learn, basically. So let's say, so this is, let's write down. So this is the direction of let's say the change of our learnable parameters. So this is direction of the change of learnable parameters, in which direction we want to change them. And here, this is the actual training or learning process. Alpha, the speed, let's say the speed or like jump length. So we have direction, and now we also have the how far should we step in that direction to change the weight. So that is our alpha. It's usually a very small constant. So you see the L, and there is a lot of stuff going in there. So we can use the chain rule to split the function graph like part by part. That's why we are not opening everything at once. If I would open everything at once, then you will need to calculate derivative. In this case, it would not be hard, but in some other cases, it would be hard, and it's not practical actually, and nobody do it like that. So it's much better to do it step by step, and then use the chain rule that just tells. So if I look at the chain rule here, so I think this part looks very familiar to what you have seen already many times. I hope that this looks familiar. So let's so transparent red, right? So the function, another function inside there, right? So and then like how you would do the derivative is here, and these prims here, it actually means the derivative of that that element. So in this case, in first element, it's with regards to gx, and the second with regards to x. So maybe I will write this quickly out and then add that equation there, so that it's more clearer. So f and gx, and then I will delete it from here. So just a second. So f gx like that, and we want this to have, this is like the kind of the function then. This is, let's say, a frac by partial with regards to x. So this usually you want to have the derivative of the inner part. So with regards to x, that would happen like so the frac. Again, then I will copy that formula in that slide and remove it here. It's just to make it clearer. So here, then the gx partial here, and this is multiplied. So let's say c dot by the derivative of x over x with regards to x, like this. So I will copy this and move it here. So to make it clearer, well, so this is the chain rule. It helps us to basically, then you can make derivative on so to split it. Basically, you can always have the multiplication between every single layer. You can just, in this case, just to make it even more clearer, you can replace, let's say, gx with some kind of, you can imagine in your head this is a b, like let's say value, I mean not value, but the some kind of temporary variable b, and you can just replace those two as b, you know, and you would have like very simple derivative there, right? So okay, that's cool. That's cool. That's cool. Okay, I'll delete this part and then return to what I was telling. So again, we don't want to open all of the equations. We want to split them by the chain rule. That's why it's not recommended to multiply everything, like to have like loss with this kind of equation and try to solve it directly. So it's better to split it. So as you saw here, the y prim is the same as this part, so we can just like leave it like this and first solve the loss function here. So the first derivative of the loss function, we want the loss function to be 0. Basically, if there's 0, then there is a perfect answer, no mistake. That is what we want. So okay, let's do that. So so let's say, so if we decide to split it, like to split the equations, then we can start by deriving the part that is interesting for us. In this case, the y prime is interesting because y doesn't change, you know, like y is the ground truth, so we don't need to derive it by the y. So y prime, okay, like that. So the funny thing is that we were talking last week at the end is that you can flip around these two and then you will have either minus sign in the front or not. So anyway, so here the one thing that's maybe not immediately clear is that you can only derive anything that is in a near, like a proximity close to the actual with regards to element. So in this case y prime. So y prime is the first arithmetical operation is minus there, and only when you execute the y minus y prime, then you execute the squared. So that basically tells you that you cannot derive directly this equation because the y is not only dependent on the squared, but also on that minus operation. But if you would like to derive only the y minus y prime, then you could do this because they are the other one is not anyhow like dependent on the first one. So to split this out, I suggest that we could maybe rewrite it a little bit so it's absolutely clear, because I think this was one thing last time that was not clear. So okay, so let's imagine that we have some new function. So remember, we can describe anything with kind of functions. So let's call this function z, and the parameter will be a, and this will gonna be the a squared. So this is our like temporary function, right? So what else then we can do is then we can rewrite this stuff as so we can rewrite it as z by y minus y, right? So hopefully this is clear, like so that I can rewrite this equation in this way. So is it clear? So if you understand so far, please like type in YouTube Live plus sign. If you don't understand, if it's not clear, then type in minus sign, and I will try to explain more. Please please do that now. That you can rewrite the squared error as something like that. Why are we doing that? So that's good. So we have some minus sign. What about others? Yes, to substitutes. You're right. No, so we're just rewriting in a different way to make it clearer how to derive it. So what about others? Plus, minus, plus, minus. Please type something in YouTube Live. So 2 pluses, 1 minus, I guess 2 minuses. Okay. Okay. So yeah, if somebody who so if somebody don't understand the derivative part, like the derivatives, partial derivatives, all of that part, so that is just tables. Basically, there are some rules where you can change, where you can calculate for any function what will gonna be the direction of the change, and basically with some kind of arbitrary jump, but basically that direction. So you calculate like how this function will change their direction, and you can calculate that using the tables. So there are rules basically how you go from that to that. So when this direction is necessary, so we can change the weights and biases, the learnable parameters, so we can fit the functions so that they can give us the desired result, you know. With regards to this part, seems like there's not complete agreement of understanding this part. So the task is to calculate this derivative, right? With a squared error function. So this is the ground truth, and this is predicted value. The predicted value comes out of our model h, and it's squared. So basically, if we don't square it, then we'll have like minus and positive values, and this is like it will not work. And but to have this derivative, we create some kind of substitution, basically some function to rewrite it in this manner, so that we understand better how to derive it. So to understand better how to derive it, basically maybe we can substitute even more because otherwise maybe you don't see it. So I want to try to make the loss function exactly as in this slide, the first like this equation that we have in the table, that is very clear, hopefully. So the idea is that you derive it with regards to one part and then with regards to the inner part and multiply it. So it's trying to rewrite it more. So let's try to rewrite it even more. So we have z, what else we can use? Let's say u. Okay, let's use u. So the u function will be this, y minus y prime, like that, right? And now this guy will be like this, y minus y prime. So now the loss function here, this equation, is exactly the same as this substituted equation, right? And hopefully now you see that this equation looks extremely familiar to here, this one, right? Fg, the input with regards to some kind of like the output, right? So the not output, but the parameter. So here we wanted to kind of derive this thing, okay? Is it clear so far? Like, can you type in plus if it's clear, minus if it's still not clear? And if it's still not clear, maybe you can even be so kind to write a small question. Okay, one clear, nice. What about others? Okay, if there are some serious missing parts in the understanding of the calculus, augstākā matemātika, then that is something that you need to work a little bit your own. Basically, those are just the tables, you know. Okay, thank you. There are some pluses now coming in. So we can also rewrite then this part again like this. So so we can use our substitution functions now here like that, and then this with regards to y prime, right? Now I think it should be clear that to solve this thing, we need to have two parts of derivatives, right, with the chain rule in the middle. So let's have this part. So the first part is the z u function with regards to u function, right? U function. And then the second part is, again, I think it's easier for you to think about it than if you replace this u as some kind of arbitrary variable. Let's think like c value or something, anything like that. So then it becomes very clear, you know. So this part, and of course the other part is even more simpler, right? So the other part is just with the y prime, and this is the u guy, right? Like that. Okay, so we have the first part, the second part multiplied, right? Now it kind of hopefully all comes together. Why the derivative is as it is. So if we start trying to replace those parts with actual those values that we have there, right? So let's see. So z is squared, right? So we can rewrite it here like so the z is squared, right? So this is oh sorry. So let's write it this part. So basically you should look at this part here, and I will just write it on the left side. So if you just open one of those, because at the end, like this small chunk of derivative still needs to be opened, in the sense that you cannot, like you need to calculate it. Basically you cannot just leave it as it is. So you don't want to open everything, but some parts you still need to open. So in this case we'll try to open it. So this is, let's say, so the z squared, right? So this is the squared. And again, I think it's very clear. You imagine x squared, right? With regards to with regards to x, for example, the result should be. So I will copy the Christopher's code. He posted something inside, and just look at what he posted. So he posted something like this. Yeah, sure, you're right. That is correct. So anyways, like we'll keep doing it my way, but what you wrote, that is correct. So anyways, nice that you understand it. So so here basically we have this guy, right? The squared, the second, the bottom part, right? And then we have the c dot of the other part, right? So we can start slowly opening the other part as well, you know, like it's not hard. You can see it with your own eyes, like just one equation above, you know. So we're opening the other part. So the key understanding about all of this is just just very simple thing. When you try to derive something, make sure that the variable that you want to derive is not dependent on some other variable. You know, like if there is something like some kind of operation like plus like multiplication something, and then there like actually the multiplication is can work, but let's say plus minus, or let's say some division, I think also can work. But basically, and then something else is on top of it, then you need to be careful to see that you should maybe split it, so with the chain rule. So basically, if you can decompose your function, that's always the safest way. You decompose the function the dumbest way possible, then you are totally safe. It will be clear, like you will not mess up. So always decompose. So here, right, now we have this part, right, and the next thing is, again, we need to just open. So let's open the last thing we can open, because otherwise everything will be opened, right? So the last thing that we can open is, let's say, so here we have this part, y minus y prime, right? And the bottom part is again y minus y prime, right? So like that. So, and now the final equation, you definitely can do it yourself, I think, because we already did this like many times, and this is like very simple. Basically, this is a power rules. Basically, power rule. Let me emphasize which is power rule. What you need to do many times. The power rule is very popular. You know, this is you can see it everywhere. So this is power rule. So if you have x over some n, then you have n minus 1, and n goes in the front. And of course, the other rule that would be it's needed is constants. So constants that you multiply always stay there. And the sum and difference rules you can see here. So they are so they basically say that you would only derive those parts that are that are dependent on the variable. So it's independent in the between. So yeah, we need only those ones. Okay. So here, this is a power rule. So let's write it in a very dumb way. So the power rule in the dumb way. So 2 multiplied by this part, and here on the square part -1, right? So very simple, right? So this is the first derivation, right? This is very simple. For the second one, c dot is then so the constant is the y. So this is a constant. So we need to delete it basically. So I know, like, what is the latex for strikeout? Let's see. Maybe I can quickly find some kind of way how to do this. Latex strike through. I think must be some kind of small stuff. So hopefully it will work. Not sure. Don't remember that I have used this kind of. So let's try to use it. Oh no, it doesn't work. Okay. What else we can do? What else we can do? How we can nicely show that this is something we want to drop. ST. Let's try ST. ST. Strike out. ST. No, nothing works. Okay. Yeah. So the this notebook don't allow me to do this, but so that's why I will write it very simple way. So there's going to be 0 because this is something we drop. Y is a constant in this case, and we drop it because it's not anyhow related to y prime. So y prime, then again, let's write it in a very dumb way. So 1 multiplied by y prime in so, and here here this is 1 minus 1, like that. So, and now we derive to the final equation, right? So this is very simple, like any person from high school can do this part. So it's just like minus 2y minus y prime, right? So now we have this equation ready. And the last trick that we need to remember is that if we would have so the y itself would be some kind of function, then we would multiply all of this stuff with the next function inside the graph. So that's how we chain them together basically. We can leave it as it is right now, and let's try to quickly make those gradients for these two guys here. Okay, but before we go back there, again, please drop in plus or minus if you understood how to get the derivation of the mean square error. Or should, like, if you don't understand something, then maybe please type in some question regarding what exactly not clear, what we can try to help. Because very soon we're gonna just make a code and make it work. Be very sad if somebody don't understand it. So it's tables, right? Tables, and then there's like just very careful step-by-step operations, remembering if the y prime or some other input variable is somehow dependent on something else, decompose everything. So okay, we have 6 pluses, 9 people online, so I guess 3 people not sure what they're doing. Okay, so let's go back to those equations here that we need to change the weights and biases, because otherwise we cannot learn anything, right? We need to somehow calculate those. So the nice thing is that we have the first equation ready, so we can just take this stuff already, right? So we can bring this stuff up here. So this is going to be same for both of those parts. So here's going to be this guy. We have c dot, so we need to somehow multiply it by the next part of the derivation, like the next function. So this is going to be here as well. I'm going to do step by step to chain them together. Basically, I will So it's not finished here. So it just will be continued. So let's, if I type in, no, can I type it? How can I type it dots? Oh, okay, I guess I can. Okay, dots, yes. So it's not finished. So it's just the first part. So the multiplication means that we need to multiply with the next function in the graph. It's a chain rule basically. The y prim here is actually the output of h function. It says just I don't want to enter here the whole large equation of age like this stuff. I'm just using the what we have here, the description of y prim. So that's cool. Then then we'll need the derivative of h with regards to weight and bias, but as I said, it's always better to decompose and split everything. So let's make it very simple way that we can derive only the part that we need from that particular equation. So let's move it down here. So now we have this equation. So this is basically sinusoid by some kind of constant, right? The r is constant, but this is a sinusoid basically. If you type in the Google sinusoid, you will see how it looks like. So to not confuse some person, I will replace all of these variables with something very like, let's say, c. So this is some, again, arbitrary variable like parameter. I'm trying to not use x or something to confuse some person. So this is just a c. Okay. So EC R, so R, we should write it here R, but basically the R is constant, so I will not write it there because this will not change. So okay, R, so something like that. So, and if we want to do this step by step by those multiplications, so like using the chain rule, we can calculate the derivative with regards to c here, and even don't care about the other parts. So I will show it. So here, let's say frac. So and if you have some questions or something not clear, then please write. This is going to be the last time, hopefully, that we need to talk about this before coding. So use the opportunity to ask. So with regards to c, so here, with regards to see this stuff, right? This is a sigmoid. We can do the sigmoid again, I guess. So we need, there's some kind of we'll need to use the I think last time I shared the rule that we need to use. Maybe I can look it up again, because on that table I think maybe it is. So okay, let me look around. Maybe, do we have it here? So one thing is that here there is a division by 1 reciprocal rule. It's a squared, so that we can use, of course. So and here's the, yeah, we can use this one. So it's actually here, so that's cool. So yeah, so we only use this rule now. Again, you need to be careful to see that here there are oh, sorry. So here there is this again, this prim sign, right? Here, right? So this means that this is a derivative of the f divided by f itself. Maybe I should rewrite it as well so that it's clear. Okay, I will rewrite it quickly and then delete it. So to use the same approach, so frac 1 over fx is the same as frac, I mean, like, not the same, but derived of fx oh man, this is fx, wait a second. Yeah, with regard, yeah, that's cool. Fx, so it would be not easy to write it, but basically, so frac of this guy, how we could write it with the dx, dx. Let's see how it looks like. Okay, frac. So yeah, I guess like that. That's fine. So like that is the same as dx of this guy. Wait a second, was it like that? No, yeah, the f only, the dx of f divided by f squared. Okay, yep, like that. Cool. So maybe with our way how we write equations, if you rewrite it like this, should be more clearer. So this is one equation that we need to use. So I will move it here. So because there's a division, right, by 1, we can use this rule. That's cool. So, okay, let's find it, how we could then, so to rewrite it, maybe some way that it's not so, not clear. So, okay, so let's write it frac. So the one thing, the R, this is like the constant, so it stays, I guess, the same way where it was. So frac. So the bottom part is squared then. So let's write it like this. The bottom part is in square, and in top part we have the C by the C, right? By the C, this whole stuff, DC, and it is like the R is basically, I think it doesn't matter like if we leave it here or the other part, because the R is just a multiplier and it stays there. So I don't like that I cannot split it somehow out. How could I rewrite it better? What is there should be some kind of latex for space. Oh yeah, I got it, space, nice, I got it. Yeah, cool. So this is good, this is good. So this part is nice. So one other way how we can rewrite it now. So I'll rewrite it then so we can rewrite the second part. So it could be a multiplication. I forgot the minus sign. Oh man, yeah, there's minus sign here. There should be minus sign. So let me see if I can back this off, and then I will copy it again. No worries, I will not remove it. So okay, like this, right? Like that, and here there should be minus sign in front. I forgot about the minus sign. Okay, so the minus sign is there. So again, like what I'm doing, I'm just using some of those rules, nothing much, just some of those rules, and trying to be careful. And even if I'm trying to be careful, I still make some mistakes. So where did DC come from? Thank you for asking questions, that's why you're there. Otherwise, you would just watch the video and without questions, it doesn't make sense, like joining live, right? So the DC is, again, this is just a substitution, you know. I'm just trying to not use the X or the other kind of variables that we have. I'm just trying, DC basically is the same as it's supposed to be integral, basically, because normally you would write the partial derivative, like, or some derivative as a division with like the bottom part sometimes you put this in both places, sometimes you use the prim signs, sometimes you use the D letter. So maybe it's not clear. That's a good point. Maybe I should use partial. But it would not be like mathematically correct way to write it. Be quite, but still, like, hopefully it. Okay, I will rewrite it now, and then it hopefully will become more clearer. So if I just try to rewrite the bottom part as not as division, but as just a like exponent. So I can rewrite this part as -2 basically. Then it will be as just an exponent. So let's rewrite it. So the first part. So this which one is free of derivatives now. So the division is free of derivatives. We can rewrite it as e minus 2 like that. So the bottom part is now rewritten. Now this is one part. So the second part, the top part, right, of the equation, top part of the equation. So the top part equation, I also will rewrite it in more like common way, so it's clearer. So the top part contains all of this stuff, right? With regards to partial C. Okay. So now okay, yeah, e minus 2, only the problem is that it should be like that. Okay, that's cool. So I rewrote it in this way, right? Hopefully now by this moment you can see that it is even so in this case again there's so you can substitute by another function, or in this case we can open this function. So the R I was thinking to open, so that let's open the R. So we should not substitute and make this totally long time to solve. So if we substitute like that, right? So hopefully now you can see that like the C variable here is only dependent on the exponent and the multiplication, and those things all come inside the rules of the derivation. So there is no, like, nothing is like holding that. And the first part of the R, this plus, this is something that we will drop it because it's just a constant. It's not anyhow connected to the C that we are trying to find. So that is cool. Let us think a little bit now. So we will have this derivation of that part. So we'll need some kind of rule how to get out the exponent. So let's look at these tables. As I remember correctly, in this table I did not find the rule to get the exponent out of there. But I remember that last time I shared this this rule with you. I will quickly get it. So this was some kind of exponent rule, or what was the name of that? So we need to access the C that is right now sitting in exponent, and we want to get it out of there. We want to derive it. So that was derivation of exponential function, basically it's called. So it seems like that you can just replace it basically. So I'm looking at it. Maybe I'm missing something. So okay, well, look, find the equation, put it, or maybe write it, maybe. So the F F. f. Okay, I will write it. Basically, I don't know where did I lose it. So anyway, so the let's again try to rewrite it. So there's a little trick there. Let us see. There's R. Okay, I almost messed it up. So see this seed here. There should not be C. It should be minus C. Sorry, that we can quickly fix. That is not actually it doesn't change anything at this moment. It will change a little bit later. So H is minus C. I will check if I here also written it correctly. Yeah, here is minus function. That is correct. So minus C here. So that is good. What about next part? So here's the minus C. Here also, everywhere where there is something in the exponent, it's a minus C. Minus C. Minus C. I guess this will also be the last tricky thing that I can explain before you get it everything, hopefully. So minus C. Hopefully I changed it everywhere where it should be. Okay, cool. So in regards to exponents, then I guess then and I'm not sure if it's a nice thing or not, but basically you can have so it doesn't change basically. So frac the exponent over, let's say, x. So this is not actually x, but just some kind of constant, right? Not constant, but some kind of variable. So frac, I mean partial x. So this is just a rule. So the rule over, if you want to derive it ex, then this is again the ex. So you can just drop the derivative basically. So that is kind of nice. So let's write this rule. But then there is one tricky thing, because there is a minus there in the exponent. And that basically means that so yeah, that doesn't matter. Let's do it step by step. So here, this is another rule. I'm not sure why it's not listed here, or maybe it is and I don't see it. No, it's not here. Maybe in that source where I copied this, it was in the separate table. So anyway, so we can use this. So quite straightforward, quite simple stuff. And the last not simple stuff will be a little bit later. So okay, let's copy this part. This is simple. I hope this is simple, right? So then the R with regards to C dot with regards to DC, this is 0, right? 0 plus R E minus C, like that. So yeah, that should be clear. That is cool. I think the last tricky stuff is that the minus part there, I think we can just leave it like that. Is that when we multiply it, it will our stuff will go in that C part, and there will be minus with it. So that doesn't, it will work. So okay. So rewrite it the last time. So minus frac. So I will delete this last so it doesn't confuse you. So frac. So in top there we have this part, right? And in the bottom part, if we just again make it as a equation without minus exponent. Should be like that. Okay, cool. Except there is some. Okay, now, yeah, I think this gonna be okay. It must gonna be okay, I hope. So I can just double check it. So you can also check it. Just type in the Google sigmoid derivative and look at the images. You know, hopefully the equation is the same, or at least similar. Basically, of course, you can open the stuff up there and then simplify the equation. Usually people simplify this equation, but I'm just interested that if it's technically correct. So just a second. I don't want to simplify it. Don't want to simplify it now. I think there is one last thing that we need to keep in mind. So E minus, yeah. So the last tricky thing is that the C is actually not the C itself, because the C will go through the function there. So how could I help you to rewrite that stuff? So let's so I don't want to confuse you too much, so I will just start from one part that we've been. So let's here. So we'll start coding very soon. Don't worry. So this is the last hard part. Okay. So okay. So technically, what we wrote so far, it's okay in case the C would be the so this would be the, let's say, first layer, first function in the graph. Then everything will work great. But this is not the case actually, because we have the our graph is connected with some other parts. Why it's not writing me? What is wrong? Ah, the frac. Okay. Okay, now it's good. Okay, with regards to part TL C. Okay, that is cool. But the problem here is that the C is actually not the C. So with regards to, yeah, that is correct what you're saying. So I mean, like, I'm just trying to explain exactly what Christopher just wrote in the chat is exactly what I'm trying to explain. So yeah, normally you would just multiply it by minus C and everything is great, but maybe we can just leave it like that. So let me think. Yeah, don't make it too hard. Let's leave it like that. Hopefully it's gonna be fine anyways. So the I'm trying to explain the thing that we will need to multiply it by minus C. Okay, no, sorry, I will just write it quickly and just in case it's not clear. So the C actually is covered in F basically, but this F is basically it is actually F. So the F function, so, and also here this is like covered with something, you know, and basically what it means is that it means that the exponent here, also we need to do the chain rule again there. So what we would like to do then is to have the exponent of the of what we did before, exactly what we did before. So that is exactly what we did. This guy. Um, and yeah, and the other, then we would multiply with regards to so the minus f, so would be the other part would be partial, so frac so as I say, basically, if you have this function as the first function in your function graph, then you don't need to do this like this chain rule here. But if it's like in somewhere in the middle, as we have right now, so this is a little bit tricky because the C is not actually like, let's say, the final output. It's again the function, you know. So this minus sign is not nice. If there would not be minus sign, then it would be just a multiplication and everything is great, you know. Now the minus sign makes it not nice. So okay, so sorry, the F, not exactly F, but minus C with the C. And here the other part was that F, and that's why it is like it is on this part. So, and again, if we just rewrite it in a very dumb way, right, we will see that this is like a so minus C, so 1 times minus C, then 1 minus 1, right? Oi, like that. So this is then the 0, right? And then this is a 1, and then this is just a minus 1. So, and if we take in account that C, so what I just wrote you is that we need to take in account that C is not just a variable, but this is a function. And if it's a function, we need to take in account the chain rule because there is a minus sign. If there would not be minus sign, we would also use chain rule, but then we don't care about that problem of minus sign. So this is a very specific case. That's why I said it's tricky, because in some other functions where you don't have that minus, they're multiplied, it's easier. So okay, here, so we end up basically with the same equation, just without the minus sign. So again, trying to make it very clear. So the first equation that we just did, this is this derivative with the h with regards to c, everything should be correct. The second part where we added the f in the parentheses is just taking account that this is not gonna be the first function in function graph. There is gonna be something before it, and if you want to use it in a chain rule, you need to take in account that the C is with a minus sign. If you would do the same thing for the positive, if there is if there would not be minus sign, you can easily imagine that after the chain rule, nothing would change because there would be 1 by C minus 1, it's 1, and nothing changes, right? So if you ever see the function graph that goes in the back, like where there is no minus sign in the front, or maybe there is just like some scalar multiplication, it doesn't change anything. If there is minus sign, it changes things. If there is something around it, it also changes things, like some let's say square, yeah, I think it's squared or something like that. So I hope this is at least a little bit clear. I understand that this is not easy to catch, but yeah. So this is one last part, difficult part. So I will move this up here. So again, the same thing is for both parts here, like right. So I'm writing here the dots. So this was the first layer, like the last layer, the last function, the mean square error. Now we have this guy, right? So we multiply it here, and now so this C, this is not nice. C is not clear. What is C here? So C, we need to replace it by what was it? What was the C? C was F, the output of F. That's why actually when we wrote it down, it was not clear in the very beginning why we need to do the chain rule there. So the F, F, F. So we'll change with an F here, like that, and like that, and like that, and like that. Oh, sorry, and like that. So okay, we'll have, so we have the second part ready. Then we'll move on to the last part. So this is really the last part. So C dot. So, and again, we use the chain rule. So the first chain rule, second part of the chain rule, then the next part. The next part we already did the last time. I think it's like even obvious to see it with your own eyes. So let's say if we want to calculate with regards to W, right? With regards to W, well, let me write it down for you just to make sure that somebody is not missing it. So we already passed the most hard parts today. So the previous equation with these exponent functions, the hardest part was, I guess, to understand that C is actually the function of C, and that's why you need to have also at the end this chain rule here. So but here this is like the very simple dumb part. So if we just have the derivative of this frac over with regards to partial W, right? So here what we get is that this is, again, let's write it in a dumb way, minus 1 times 1, and this guy is just a constant that is multiplied, so we'll leave it, and what we end up is v1 times x is x, basically, right? So we end up with this guy, so this is great. And for the other part, for the b, so I will go down here so you can see it. Sorry, like here. So for the b, we can write it like this. So let's say again, so C, some kind of constant. The constant is basically the g function, right? So let's write it as a g function there. Plus b, right? So the b then is, so if we again write it in a dumb way, minus by minus. So it's at the end, so multiplied by minus, of course. So we get 0 plus 1, right? Plus 1. Because the g function is not any way related to the b, right? So that's why you can write it like that. And the output is 1, right? So we have all those two guys also ready. So one is x, another is 1. So very simple. So with regards to these two last, everything clear, plus, not clear, minus, some question, minus. Just write in some question if it's not clear. If it's clear, plus. With regards to those two last, if maybe something really not clear with the difficult with the exponential derivative, then please write very carefully the question, and I will try to explain. So at least two pluses. I think these two equations, these last ones, these are really simple. You know, like you cannot get simpler than that, I think. Like just so that this is a power rule, you know. Could you show the L derivatives again? Okay. So the L derivatives is here. So again, so in this case, so maybe you're thinking about the y prim and the chain rule. So because it's again also the function. So y, and here this is a minus here. And we actually derive it directly with the y here. Okay, higher. Okay, not sure. Ah, you mean this ones? Okay, I did not yet added the parts. So here we need to have x, right? The last part, and here we need 1. So now we have the full equations of calculating the learnable parameters, right? How could I? Maybe I will just I will add on the Jamboard these equations. Of course, maybe there is chance that there is some bug, but hopefully not. So let's see. So I will add. So these are actually the equations that we need to train the model, right? So it's copying, copying, copying so long. Hopefully it will copy. I had one situation that Jamboard stopped working and the Google Classroom did not accept to upload anything. Hopefully this is not the case. So it's loading, loading, nothing happens. Oh man, this is not nice. So I will try it again. So I have this equation, trying to copy it. So something happening but not showing up. This is weird stuff. Okay, it did not copy anything. I tried last time, so if it will not work, then maybe I just need to share the notebook with you. This is not normal. Okay, the Jamboard seems to be broken, or I don't know what's wrong with it. So anyways, I will share the non-editable notebook so you can copy it if you want. I will drop it in here in the chat and also inside the classroom. So, but to avoid situation when you're not doing anything, I will just make a copy and continue working with in another notebook. So just make a copy, copy, copy in the drive, save a copy, creating a copy, open in a new tab. Okay, cool. So I shared you that notebook. I don't know why the Jamboard stopped working. That's stupid. So anyway, so we have the model, we have the loss function, and we have actually the equations to change the weights. So now we start coding finally. So again, so it's not connecting. Hopefully. Sorry for the mess. I will try to be more. So okay, code. Okay, cool. So import numpy as mp. Actually, we don't need numpy, I think, in this case. So we'll use. Okay, yeah, the numpy. I'm not sure. Maybe we'll need it. Numpy as mp. Okay, cool. So in this case, let's write this stuff more optimal. So let's write it. So the x is going to be our input data. The x input data is 2 floors, 3 floors, 5 floors. Y is 1.5, 4.5, 9.5, right? Cool. So the function graph itself, let's write it out. So I will move these equations up here so I can follow them. Just a second. Okay, so the function graph itself So this is going to be with the, so let's write it similar way as the last time, so it's clear. Even you can use the same functions basically for some of those things. So here is going to be x and y, so the g function, right? So this is like return x times y, right? Then def, the next one is f x y b return. So nice thing is when you get through the equations, it's really simple to call it very fast. I would say x plus b, right? So and then and def h x. So the h1 is x v b r. So r is actually, we can write it here as np max of y. So that is a constant. This is our kind of limit of our prediction capability, like the maximum value that we're gonna predict from the sigmoid. I mean, like this is just a specific type of model that shows the function graphs. It shouldn't, for other models, maybe you don't want something like that. Okay, so this is then the return. So this is going to be return of r divided by 1 plus np exponent of minus f. It's very nice that the Python now allows us to write it in a very similar way that we had in the equations. So the h actually is y prime already, so that's great. We have the h as y prime. And we forgot about the y and weight and bias, right? So let's initialize weight and bias in some kind of some manner that would be appropriate. So weight definitely, so I guess we can initialize them by 0, and then it's very nice then to debug it. So if we initialize those two by 0, then basically we can see if they go in some positive or negative direction. And also the bias actually is always initialized by 0. So okay, that's cool. So the last thing, okay, we need the loss function as well. So def loss function, right? So this is going to be the y prime. I could actually write all of the stuff that we had before. I could do so. Let's keep it by the same approach. We can. It doesn't matter. Basically, you can imagine that you can pass Python either in this way or the other way. So y minus the h of all of this stuff and squared. Okay, cool. Loss function ready. And now the derivatives, right? So we actually are interested only in two derivatives, dy, right? So also let's write those as a functions probably. Probably write them as a functions, right? Let us think. Yeah, let's write it as a function. So let's write it as a function. So def. So because for every single type of inputs, like for the first one, for the second one, for the third one, we will have different kind of derivative value. It will be always different. So dv L with regards to dv, with regards to v, L with regards to v basically. So this is going to be all of the stuff that we need, right? And we can just use the, okay, I have a mistake here, nobody told me. So return, so all of the stuff that we wrote before. So minus to y, so here we need the multiplication sign, y minus the h, so we can just put it here like that. This is y prime basically, multiplied by the first part of the r multiplied by np exp minus f x vb. So this is the first part, right? The second part divided by 1 plus the same stuff and only squared. So this is the second part, and then multiplied by the x. So this is going to be with regards to v, and then the last thing with regards to b, and there is at the end 1, right? So now we kind of have all of the equations that we need. So type in plus if you're ready to move on, minus if you're still working on it. If you have some problem with this, then also write it. So I will just copy this and in the background double check that I don't have some errors, so you can keep on working on it. Just type in plus when you're ready to move on to the training part. Okay, at least one person ready. Let's wait for somebody else as well. So I'm just checking out if I don't have some errors here. Okay, I found one error here that I don't have the semicolon. So I have 4 people ready. Let's wait for somebody else, someone more. So somebody is still fighting. Okay, good. Try to do this. Just a second. We'll wait a little bit. Okay, so we have quite a few pluses. One thing that as I think like would be fun to do now is if we have numpy, we can I think we could do all of the calculations at once for every element here. We could imagine that this is our mini batch with 3 samples. So that's why we can rewrite this as a np array. Just add array around this. That just will make us be able to execute all of these functions for all of these elements at once. So we will not need to call x1, x2, x3. We can call it once and it will execute so this is going to be at once the kind of our mini batch, as you might say, you know. So that is one thing that we're going to use. So then let's make some iterations for the training, you know. So this is going to be our iterations, or let's say call them epochs, you know. Because in our case, like all of our data set is just 3 samples, you know. So range 10. So we're gonna look at all of our data set basically at once. So we generate let's say y prim. Now we can generate this directly immediately from the h, right? So from the x, I mean, so we can use the large X here as the input. We can use the so what else we have there? You can use the VBR, right? So just to make sure that it works and there is no error, I will just write it like that. So the outputs. So let's write it like that. Plus, also, I would like to see what is actually the y that we wanted to calculate, and what is the y here. So the x and y. So this is the inputs, this is the ground truth, and this is what's predicted. So I will also break out because we're not doing anything yet. So I'm just trying to run this small piece of the code. So now what we have. So these are the inputs, these are the predictions, and these are the ground truth, and this is the predictions. So the predictions are nothing right now. So this is completely wrong right now. So that's fine. The next part then Let's calculate the loss part. So loss. So the loss will be this function. Again, let's replace this by large y and large x. We will again, we can, of course, we can have another loop there and calculate this for every single element, but numpy is a very nice library that it allows the vector math to happen for every element at once. So it will just use the same functions for every element automatically. So the loss, so we'll add also the loss. So let's see if the loss works. So if I run it, so we can see how bad is the output. So let's say the first one should be 1.5, this 4.75, the loss is like that, very large. The middle one is very close actually to the real value, and it's like very small loss, so it seems like that it's working. That's great. So the loss works. So the last thing we need then is to calculate derivatives, right? So the d with regards to w. So calculate this. Again, let's use the y, x like that. And this is not going to be that easy, I think, because dv, of course, will not going to be just a single value, but it will be actually the vector, because we will execute it over all of them. Okay, so there is a problem. Okay, like that. So like that. Okay, now we have this thing. So we have it, right? It's actually good to see those values, because in that way we can estimate what should be the alpha, our learning rate, or the speed, or the step, you know. So we'll see that this is a vector of 3 elements for the let's say the derivative with regards to for the every element, right? But we need the one value, because w, if you see here, is just a scalar value of 0. So what you suggest, what we should do to apply this w, dw to the actual w, like what? Please type in the YouTube chat the code, piece of code, what we could do to, in your opinion, how we could change the w if we know the alpha. So let's write it alpha. So alpha will be, in my opinion, let's say e minus 2. So what is going to be the code? Somebody please who understand it, or at least try to write this one line of the code and drop it in the YouTube chat, okay? I will wait a little bit. So you can see here in the output actually what is the output, right? And my question is how to change this weight. So because you know, like the formula is okay, probably, hopefully, but there you have 3 dimensions, right? Like you have 3 elements. What do you think? What would be the best way? Okay, so at least one option, right? So if you write it as you wrote in the chat, so don't worry about minus plus. So we already discussed this in the chat. In the chat, it means like basically when we discussed it with Johannes Hoffman is basically you always need to use minus basically if you want to minimize something. It's just in that case there was like misconception with regards to loss function. So anyway, don't worry about that. But the problem is different. So the equation that somebody like from the YouTube name, I cannot tell which one was it. If you want to write your real name, then I can say you. So anyway, it will not work basically because the w is a scalar value and the dv is vector. So please, somebody else, can anyone think of what we should do now? this should be quite easy task. You should just a little bit think about it. What do you think should be logical approach, what we should do? So if you don't understand completely what to do now, then please write the minus sign inside the chat so that I don't just sit around and wait forever and nobody will do this. Nobody wants to also say that they don't understand, right? Get a module. Okay, so nice. Now we have some ideas coming in. That would not be correct, unfortunately, because remember that derivative basically is direction, right? We don't want to override our direction, you know, like if we just make a module, then we will like override our direction, you know. That would not be optimal. So maybe some other ideas. So okay, thanks for putting on minus, then but maybe somebody else have some ideas, or everybody is minus right now. Yeah, nice. Kirill gives some idea. So why we could not calculate the average value of those three and then apply that to the weights, right? We could do. That is good idea. So let's calculate the average value. So that if you, in a sense, you could think about this in this way. So if you have like three directions, okay, we have three directions, right, of the three different samples. Now if we calculate the mean direction, it will be something in approximately to all of those three directions, but it will not be exactly the same direction, you know. So, and that is correct. So let's write it as Kirill advised. So let's write it W minus NP mean dv. So the mean is basically average, right? We can write it as average, average. So maybe somebody is more familiar with something like that. So and then multiply by alpha, right? So this is done. So we have one stuff ready. So then we also need to calculate with regards to bias, right? dB. Again, the same equation, right? You just copy that, dB. And now we'll see if we have a bug, you know. Hopefully we'll don't, but who knows, who knows. So, okay. Could I see your f function? Sorry. Okay. But the f function, you can look at the equation. It's like so simple. You should write it yourself, you know, like it's just a g plus b, you know, nothing else there. So okay, so I gonna, so this is the f. I'm gonna run it. So let's see what happens. So I will also print out these derivatives and also the weights and biases, because I'm scared that maybe there's some kind of bug. But if I will see those, then there's a higher chance to understand what's happening. So normally when you write like large models, you would use some programs that do this for yourself. Okay, we have also some very not nice problem that loss is also three-dimensional. Of course it's three-dimensional. So, but we would like to have one value that says us what is the actual the average precision, you know, let's say. So NP average of the loss, let's say. So that now we actually so we converted from squared error to mean squared error. Okay, so mean squared error. So that is the average value. And also I will comment for this case this out and run it again. Okay, it works. That is great. That is great. Yes, but my error is throwing an error. Error, cannot read it. What is the error? So one option is that you can make some screenshot and upload somewhere or something like that, or some snippet of code and share it in the chat, and then I can help you out with the error. But basically so maybe you forgot in the top part to make X as an NP array. If you don't change it to NP array, then the list will not work automatically with this kind of operations with the plus and the exponents. But otherwise, you can see that it is actually working. The code is getting kind of the output is getting better because the losses getting smaller. So maybe I don't know like what will happen. But let's add let's say 50 time steps, like 50 epochs. Let's run it again. So with the 50 epochs, now it's getting much better. So let's add 200 epochs. Maybe we will start seeing bouncing, you know, when it goes to the loss to the very bottom and then back. So actually we see very nice values. This is beautiful. See, the last predicted values are something like this, right? Very nice values, so very close to the real, like 1.5. Okay, it's not very close, but it's much better than the very beginning where you just predict for all of them the same value, you know. Okay, cool. The NP array problem was. So is it working for you? Like, is this code working? So is there some problem? So then just type in. I also run into the problem. So NP array. Remember to add NP array here in top. If you have some problem that you can easily share me right now, just make a screenshot, upload it somewhere, or send me some snippet of the code. I can help you. So let's say that one person is happy that it's working. So what about others? Can you type in plus, minus? Is it working for you? Basically, we just made a workable, like really cool small model, you know. So the task for those guys who this is working. So let's try to predict what will be the y prim. So what will be the y prim for x? X is 4. So when it's not going lower than 9.4. So if for some reason you cannot, it's not getting smaller the loss, then it might be that you have some typo in the equation somewhere. If you have some typo, then basically you will need to carefully, like, so I will scroll it now carefully down. Then you will need to stop the YouTube and then carefully compare with your code. Because you see it's like very short code, so it should be able to get it working. You remember how long equations there was, right? The code is so small, you know. So I'm just scrolling slowly down, and those guys who have finished, they can try this example, right? After the training. So let's say, so this is going to be the y prim of the let's say this is going to be the let's say some kind of production version, right? Where you would like to use this your cool model for predicting some things that was not actually in the dataset, right? So if we add here the 4-story building, you know, so we have X as 4-story building. This was not included in the dataset, and we want to know what will be the price of 4-story building that was not in the dataset. So we will see what the model thinks the price should be, and that's, I think, quite interesting. So okay, so for X price should be y prim. And see, for production models, you actually don't use loss function anymore. because you don't have ground truth, you know. You don't use the derivatives because you cannot change anything if you don't have ground truth, you know, right? So if I run it now, okay, I have some typo. Oh, where is my typo? Print, right? So otherwise everything is working excellent except the typo. So okay, funny, I got some kind of 3 outputs. Why I got 3 outputs? So x y print, okay, sorry, I used the wrong value here, y print prod. Okay, so run it again. Okay, cool. So if we see that for the 2-story building, the ground truth is 1.5, then the 4.5, 9.5, the output is 4.6, 8.5, 2.29. Basically, it's actually converging. Basically, if we run it even longer, it will get even better values. And for the 4-story building, it automatically predicts that the value, that the price will be somewhere in between those two things. So funny, the Christopher says that after 1,000 epochs, it will get you very good values. So anyways, so so those of you who had some problem with this code, I remember I went around this very slowly to scroll it over so you can check it out, right, and see where there's problem. And now, like for the last, like just to refresh your memory of what we did before and what we're gonna do the next time and what's gonna be the center of our studies. So I will just show you again so those guys who have some kind of problems or anything like this, so you need to check the code carefully yourself, but the logic is kind of okay. So there was the workshop notebook that we started doing, and no person actually submitted the tasks that I was asking to do. So after this today, I will share my notebook, and I will also again give you the same task as it was before, and hopefully this time somebody of you will be able to actually finish the task. So so for our like kind of structure of how we build the models, remember that we had those remember there was a weight, bias, right, the actual x, so the x y prim. So actually, if those guys who write like research work with me, they should definitely pay focus, like try to find time and do these homeworks, because otherwise, like you would like to build great research work, right? If you just skip those, it'll be even so much harder to do anything good at the end. So anyways, so here these are like those things that you already saw in the equations, right? For all of these guys, we're gonna use the class called named variable. So these are like for all inputs in functions, and actually inputs and outputs in functions, we will use variable. So this code, this template, I will share it again with you. So that was from the homework. So just for those guys who want to, for the last let's say 10 minutes now, to continue following what we do, I will drop this template inside the classroom. So drop it in the classroom. Trying to find where the code was. Where is it? Ventspils, right? The so this is the 3.1, I guess. 3.1. Okay. Oh man, accident. I thought that I can just drop it. I cannot. File. Trying to drop this on the classroom. So okay, copying to 2 kilobytes. Okay, on the classroom wall, it's now available there. Okay, that's cool. So anyway, so the variable is for all of those inputs because so you remember that we calculated the W, right? So let's say this is W, right? And the grad is actually dV, right? So we need those two things, right? So we can change the W. We need also the gradient of W, the dV. So these two things are encapsulated in this class. It's always good to keep them both together because in most of the equations, the value here appears also in some manner of the form inside also the like the derivatives, or at least in the like the next derivatives where we use the chain rule. So that's why I always keep those two together. So this is one element. The next element is then the linear layer, right? So the linear layer, there is the weight matrix of this. So the one thing that's different from our equation that we had today in our lesson was that today we had weight as a single scalar value, but what we want is weight that can have I mean the weight and x and everything, that basically, so that can have many values. And we can say the same thing about x, for example. X, right, we had the single value, we want to have many values. Y, single. So what I mean by this is, let's say these many values is the in features, out features, okay? And what I mean by this is that let's say we have the floors of the house, but we want also to take in account for price prediction, let's say year built, right? When it's built, then we can take in the price like number of rooms, you know. So now we have three-dimensional vector that is just x, and to handle three-dimensional vector we need also three-dimensional weights. Maybe we want not to predict only price, but also, let's say, how I don't know, like how good quality is the house, or something like two values at once. So that's possible. So the linear layer is actually the equation of the linear layer is, let's say, something like this. So f x wb, and this is w times x plus b, right? So basically the same as we did before, is just we combine two together because they always use together. Basically, this is also called affine transformation. And also the one thing that for those guys who were following our workshops from very beginning, we use linear algebra tricks. Basically, we use the dot products that are matmult here, and we can change the dimensions of the vectors. So the idea is that in features are incoming dimensions and out features are outgoing dimensions, and that happens because if you look carefully how the dot product works when you multiply it by matrix, if you multiply it like the in features here and the out features here on the rows, then you will get the columns of the out features, basically, and that way, like you can change the size of your basically your vectors. So the forward is here, that is good. The backward is here. So they are already the derivatives. These are the derivatives. So maybe I can rewrite it. So here the dB, this is 1 basically with regards to that equation up here, right? This is 1, and it's multiplied by the chain rule grad, the same thing that we wrote in the equations today. So the v is actually the x multiplied by the chain rule, right? And x is W by the chain rule. So it's funny that we need to calculate also for X, because the linear layer can maybe not be the first layer, it can be somewhere in between, and that's why maybe we would like to have the gradient flowing also to the X. So that's what. The last thing, I will also make a breakpoint here and double check that I don't have some kind of bugs here. So see, I made some dummy function here. I created the random stuff here, right? So if I just run it as a debug, hopefully it works. Maybe there's okay, we got it. So the dummy function put us here, and let's see what we have here. This shape. So this is 32 by 2. Let's see, 32 batch to output. So the batch, remember, what is the batch? The batch is X, the sample X1, right? The sample X2, and so on, right? So we can calculate even to the whole data set at once, you know. Maybe in some cases it works, most cases doesn't work. It's always better if you have high dimensional space to go by smaller steps. So this is actually the batch, basically. If you don't get it, then please go back to the video and try to look at what we did today. So that part, so these are the gradients. So again, this is actually interesting thing that you need to keep in mind. So see, out features are two-dimensional, right? So what shape we have here? The shape that we have here is let's say, so this is a batch by out features, but the B itself shape, the B shape, so let's write it like this. So B value is just out features. So, and here we can use what Kirill law suggested, where you were stuck for a long time, is that you can just calculate the average value over the batch size, right, of the out features, and then you can modify the B value, right? So that's cool. So the gradients should be clear. So if I remove this part, and let's go down now. So let's see what does there. So we have this, so we have mean square error. So for mean square error, again, you need to implement yourself the forward pass and backward pass. You should be able to do this now, definitely 100%. So, and then you need to, I guess, link it together, basically. So maybe let's extend the task a little bit. So the mean square error part, right? What else you have here? So you have actually the dataset here, in features, out features, and then you don't have model yet. Okay, cool. So let's write some other stuff here. So I will also later maybe post this template so you know where to start working. So this part is still the dummy code so far, right? So this is dummy code. Loss, okay. So you will need also to implement the let's say class. So we already did this today, by the way. So the sigmoid. So this is we will need this function def init. So the sigmoid we implemented today already many times. So self here will be the x. We'll need this one. I think we'll need also the out value. Wait a second. Yeah, output. Self output none. And def. Actually, what I propose to you to do is to do what we did by hand, but just using this structure. So forward x, here is going to be the x variable. So this is going to be variable type. I'm just leaving it here because so that you don't forget it. By the way, yeah, so this is going to be the return self output. Then you will need to calculate this here. So here you will need to calculate this to do. Okay, and then you'll need to have a backward pass, right? So this is going to be pass, and here's going to be to do, and your model basically will be following. So the model will consist of the linear linear. So, and we can actually make the same data set as we had in our today's session. So you just need to make it work using this structure. So what was there? The x was 2, right? So this is going to be np array. So this is going to be I will put it with the extra parentheses because it will be one-dimensional stuff. Okay, so 2, 3, 5. So like that. So this will give us the shape of 3, 1. So the in features are actually 1. So the out features, actually also maybe better to have the floating point numbers here. The out features then 9.5, 4.5, and 1.5, right? So these are the out features, right? So again, one dimensional. So on here we'll write in features is 1, out features, let's say in this case that's going to be fun. We can make it that out features are 4 now. Then we'll have layer sigmoid, I wrote it the sigmoid, let's call it layer sigmoid. So this doesn't take any input parameters. So again, 4, 4, layer sigmoid, and then linear layer at the end. So if you want to create exactly the same model that we had before in the session today, then you can modify the last layer with the sigmoid with the R multiplier, you know, but it's not definitely necessary. So basically what you're going to do then is you need to pass to inside some kind of for loop to get the y prim. So to get the y prim, you will need to call, let's say, so this is going to be something like this. So out, in the first case, this is going to be none. Let's say for layer in model, and we'll call layer forward. So this is going to be the out, and in the first case, this is going to be x, right? Like that, out, and here's the out, right? So that's how we calculate the go through all of the functions step by step, right? And in the same way, at the end, you can calculate the loss, right? You can calculate all of the derivatives. So derivatives you would calculate then. So then you would calculate to do calculate loss. And then the last thing is you would calculate derivatives, and that you can do very easily by reversing the layers. Reversed. I will share this code, so those of you who are not familiar with it, you can then familiarize yourself. So backward, so we start by the last layer and then go to backward, right? Something like that. And then basically in those linear layers that we have, so you can access the gradients. So let's say, so this is going to be the model first layer. We'll have W there. I think there was W, and here's the grad. So this is now calculated, so you can use it, and you already know how to use it. So basically, remember that you also need to call first the loss backward. Basically there you will have loss function backward. Sorry, loss function, and you will have the loss value like loss function forward. And there you need to do something here. So inputs, to do. And loss function is basically our loss MSE, right? So is it clear so far, the tasks that you need to do in this template? Is it clear? Then plus, if it's not clear, minus, and that's the last thing we do today, and we end. If it's not clear for everybody, if you post minus, then maybe ask a little question regarding what is not clear, what we need to do. So basically, I will give you a template with the structure of the code where the value and gradient is together in the same same object, right? And you need to basically make a little bit smarter model than we just wrote in the notebook, but using the elements we have in this template. Basically, the forward passes is just like calling functions one by one, the same way as we had in our notebook. The backward passes is also the same way as we had in notebook, but calculating gradient with regards to every like function and then multiplying with the chain rule together. So the multiplication part, just to clarify you again, is here. So if we go to linear layer, you see there is a output grad multiplication, output grad multiplication. So I see only one plus. I will share the template. Hopefully it will get clearer when you look around the code and compare it to what we did today. I will also clean this template a little bit up so it's even more precisely as we did today. And I really hope that till the next time, at least some of you will be able to submit the homework of this template. If you will not be able to do this, then I will be forced to show you everything in detail again. I hope that that basically you understood the basic concepts. Okay, so thank you for all of joining. I hope that this was useful. I know that some people already are doing like a subscribe to do research work with my team. So for the bachelor's, master's, so if any of you still interested on that, then contact me on WhatsApp, or I'll give you some topics of research that we do. You will need to work hard to understand all of this stuff, but at the end you will be able to do cool things. So that's it for today. So meet next week. Okay, bye bye.